OK， 好。All right, so welcome back. Let's continue our lecture. So chapter 5 is really difficult. Okay, the most difficult chapter in mechanics of material. All right, so we need to focus more compared to other chapters. All right, so last time we talked about the property of cross section. As you know, our beam, our material has side view and cross section view. All right, so because you can see that this moment is kind of bending this material, something like this. So you can, if you cut a cross section like this, all right, you can imagine that there's a bending, kind of rotating that cross section. Okay, so that's the reason why we are going to discuss cross-sectional area property, because our bending moment is actually acting on that cross-section. Okay, our shear also acting on that cross-section. So that's the reason why we are going to talk about cross-sectional area properties. And the property of the cross-section, the first one is first moment of area and the inertial moment of inertia. Okay, so the first one actually related to centroid. And all we need to know is that when we discussing the area distribution respective to certain axis, okay? 面积对于某一轴的分布。When we discussing this, the distribution of area to certain axis, we call first moment of area. All right. So you see the definition of this is actually area times its own coordinate to that axis. Okay. So when we do that, we can determine if we did the value first moment of area, we determine that value, and then we divide by the total area, which means that the area average distance to that axis. So actually, it's the centroid of that shape to that axis. 可以帮我开个冷气吗？我已经开始流汗了。啊，在这里。交给你好了，不是那么容易的事情。谢谢。All right, so this is the first moment of inertia. It related to centroid. All right, and the other things that typically we will determine the area you have by using combined method. All right, so you determine each area that you know where is its centroid. So this is centroid in this rectangle here, and you can determine you already know that the centroid coordinate. Okay, you have two areas or more, and then you times its own area and its own coordinates, and plus them together, divide by the total area. You will get the centroid for combined area. All right, so I believe you know this, and also you can use the negative area to have alternative way to solve this problem. And then we enter the second moment of inertia. The moment of inertia, we discussed that before, right? Moment of inertia is the definition of that is that your shape, how difficult of that shape rotate about certain axis, right? And the easiest way, 可以帮我按那个绿色按钮。The easiest way or the lowest way, lowest moment of inertia is that the axis through centroid. Okay, so you can see that this centroid, this axis go through the centroid will has the lowest value of the moment of inertia. Whenever you move that axis to other position, it will increase the moment of inertia value. All right. So you can see that this is the parallel axis theorem. Okay. So if you have a cross section, you bend it, not necessarily always through the centroid axis. You may go to other axis you want. Okay, so you can see that if you are going to move the axis to a new axis parallelly, okay, you need to add in area times the distance difference between the two axes and square. So this is the quick example that the green axis penetrate the centroid. So it has 12 BH3, right? BH3 would be BH3 over 12. And if you move to the edge of the rectangle, you need to plus the area BH times the distance half h square. So you can get the BH3 over 3. Okay, so that's how we move the axis. But be careful, the parallel axis can only be applied through the central axis. So you can move from green to pink, but you cannot move this to here. You cannot do that. You cannot move from here to the green to the pink, because this proof is based on the green axis property, because only if you start from the green axis, you can have this term become 0, right? If you start from here, no, you cannot do that. You always start from the green axis, which go through the centroid. 好，这边讲中文就是说，我们不能随便乱移说，就是这个式子不能随便乱说啊，我要从这边移到粉红色，不行哦，你只能从绿色移到粉红色，或是绿色移动到其他的地方啊，其他的地方往上移往下移都可以，但是你不能从别的地方移到粉红色，你的起点一定是要是绿色的，为什么？你中间这个项是因为你是通过行星的轴，你才会为零哦。那如果你是从其他的地方移的话，你这一轴就不为零哦。好，这边要小心。好，所以你一定要从绿色的移。Okay. Now let's continue our lecture. All right. So after we discussing the property of cross-section, we are now suitable for discussing further about normal stress in beam, normal stress in material subjected to bending, okay, bending or shear, okay. So assume the material is linear elastic, okay, good, okay, and then from Hooke's law, you know that sigma x equal to E times epsilon x, yeah, chapter 2, chapter 1, right? And now we apply here epsilon x equal to minus y divided by rho. You know that, right? And also the 1 over rho is the kappa. So it's minus E kappa y. So you know that. And so you can see that sigma x is actually proportional to y and with the negative part, okay? Negative sign, sorry, negative sign. So now if we have a bar, okay, and we has a bending on it, okay, and I want to know that certain, just cut it. I want to see that this surface, what is the normal stress on that surface? Okay, so I enlarge it. I enlarge it. Okay, I enlarge it. And you see, here is X, here is Y. So it is side view, right? This is side view. So don't think this is a cross-section view. Okay, careful. Sometimes you see, oh, it's a rectangle. It is cross-section view. No. This is side view. You need to focus. You need to know X and Y axis. Where is the XY axis? All right. So you see that here we say this is the axis and this is a point O. Right. So what is the, we say this O here is the neutral axis, right? We said that after the bending, F and before the bending, the neutral axis won't has any change of length, right? So which means that its shear, its normal stress is 0, right? 我们记不记得我们之前不是说过，如果今天有一个材料受到弯举，然后它有一个位置，它是弯前弯后不会长度是不会变的，那弯前弯后长度不会变，表示说它没有任何的 normal stress， 没有任何的垂直应力嘛，对不对哈？因为它没有垂直，没有应力啊，没有应力，那它就不会变长或变短啊，对不对哈？所以这边这个 O 一定是从零开始 ，OK？ So as we mentioned that neutral axis, no change of length before and after bending, so it starts at 0. Okay, no shear stress, and the shear stress will be related to the proportional to negative y if we have the positive moment, positive moment, yes, moment, yes, right. So you can imagine that the y here is getting higher and higher and higher, right? So the shear stress will be like a triangle. Okay, like a triangle. The bending moment. So you can imagine this bending will kind of compress the top and elongate the bottom. Okay, and the neutral axis, no change, right? No fault, no stress. Okay, and you see, because negative kappa y, right? Sigma x become negative e kappa y. Y from the below the O will be negative, negative, negative. So it's positive. So the positive will make the bottom part of the material become lengthening. Yeah, tensile. 所以你可以看到，如果今天你是一个 M 是正的 moment 在上面的话，你在中性轴之上，它会是正的 Y 嘛？那正的 Y 它这边就是多一个负号，所以变成是压应力，而且Y 越大，它的 sigma x 会越大，所以它就变成一个倒三角形的应力分布。然后呢，下方的话 Y 是负的，所以负得正，所以它就下方就是拉应力，然后就是越下面就会越大。OK， so I guess you quite understand. I believe you understand that, right? So if you have a pure moment, you will have a stress distribution looks like this. Okay? So now let's talk about where is the neutral axis exactly? Where is the neutral axis? Because neutral axis is so important, right? Because this O is starting, this stress distribution start at the origin, right? So we need to define this. So actually we don't know. We will give you a answer, the answer next page, all right? Again, this, the proof to show the neutral axis position is also follow 95% of the proof in mechanics of material. We just times stress times the area become force and do the force balance and you'll get the answer. Okay, so it's not too difficult. Okay, let's do it. Location of the neutral axis. Again, can I give you a bonus chance? Can you tell me what is the view, side view or cross-section view? Here, what is this, if this is side view or cross-section view? Can you tell me, please? Please first. Side view. Cross-section view. Why? Why? You are right. Why? Axis. 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 So you can see here is Z, right? Z is showing the cross-section view. Yeah, exactly. Very nice. Okay, can you tell me the number? 11613 024. Very nice. So yes, exactly. When you see the X, Y, X to the right, Y to the top, it is side view, right? This is side view. And if you see the Y to the top, Z to the left, it is cross-section view. Cross-section view. Okay. Well, this is relatively easy in this case because you never see a bar looks like this. Never see the bar looks like a trapezoid shape. Okay, this is a little bit. So you know, this is cross-section view. But sometimes you will see a cross-section like this, rectangle. So you will you see these two are very similar. So you need to identify this by the axis rather than the shape. All right. This is quite important. Okay. So again, you know that now we are going to define this neutral axis. Okay. And you know that if you have a material subjected to a pure moment, your shape, your stress shape will look like this. Look like this. And this is a compression. And this is tension. Okay. Now, we see this cross-section O here as this one. Okay. So the axis actually go through to you, go toward you. All right. And of course, this trapezoid is actually an example. All right. This is an example. Please don't memorize. I mean, actually, this is just example. You can choose other shape. All right. But well, just saying that this proof it doesn't go with this special shape. No, it is general because you do the integration for area, right? So the area can be an arbitrary shape. Okay, so let's continue. So you can imagine that this moment here will give you a force this moment will give you a stress, and the stress times the area will has the force, right? So you can see that top. You can imagine that all this stress is kind of, how to say that, pinching this area. Okay, so pinching this area stress times this dA, it will have a force pushing the upper surface into the monitor. How about the bottom? The bottom is here, right? Bottom is go tensile. The tensile will be make this area go toward you. Okay, so this stress will kind of drag all this small dA toward you. So you can imagine that there's a force here toward you, and there's a force into the monitor. But this area is still here, right? So which means that they need to be balanced. So actually, you see, sigma x equal to minus E kappa y. So this sigma x is this for equation is the formula describing all the stress in this area, right? So you do the integration for dA, so you can imagine that sigma x times dA times its own small area, and then do the integration. So yeah, sigma x, you substitute in here, and you can get this one. Okay, so this is the force. This is the force, and this force is actually combining the force here and the force here, and this one is going to the monitor, and this one going toward you. Okay, so the total force in this cross section, you need to follow sigma fxy equal to 0. So the total force equal to 0. Okay, right. So if E and kappa are constant, E and kappa are constant, so you can go out of the integration. So you take here out of integration, and also because this is equal to 0, so E and kappa can be deleted. Okay, so and minus can be deleted. So all you left is y dA integration A equal to 0. What does that mean? This is actually the formula of centroid. Okay, you recognize, right? You recognize this, right? So this tells us the neutral axis is at the centroid of the cross section. Okay, so our answer is simple. For the area, where is the neutral axis? Centroid. OK， 听得懂吧？哈，一样啊，哈，就是 moment 压上面跟拉下面。那压上面就会有应力嘛，那应力乘上它每一个小dA点，就会是上半部的应力，上半不好意思，上半部的力，那它就往内推啊，然后往荧幕推，然后下半部是拉嘛，然后它的小应力乘上它的dA，就是它下半部所受到的力，下半部的力是往你们这个方向，所以说荧幕出荧幕的方向。所以一前一后一定要 balance， 不然的话这个东西早就被撕裂了嘛，对不对哈？那它就不会让你放在这里。那所以说它的这个 fx 在哪里啊？在这里啊，x 是这里嘛 ，y z x， 所以 x 的方向的力是要平衡的，所以你这样子 积分起来以后，你就会变成这边等于0啦。All right. One more things that one more mark. Epsilon kappa can go out to the integration, and then minus sign kappa and E will deleted by the 0 of the right hand side, and all the thing left is this one, and this one means centroid. Okay, so I believe you can know this. Right. So now we determine the centroid and the neutral axis location. So let's further connecting the moment and the shear. Moment and the stress. Okay. So you see there are plenty of stress, right? Sorry, you have plenty of stress here, and this stress caused by this M. So what value M will correlate to the sigma x value? We are going to see that in the next page. All right. So moment curvature relationship. Why we are going to discuss moment and curvature? Because there's a curvature here, right? Curvature and so if you correlate the curvature and the M, you can correlate sigma x and M, right? So there's a purpose. So again, it will looks like you are going to integrating the moment and the stress to make the stress times its own area. Okay. Again, you imagine that this shape is subjected to a moment from here out to the monitor and enter the monitor. Okay, out of the monitor and enter the monitor. Okay, so kind of looking like this. Okay, so this dA is the bending moment or on a small area. So this moment of area. Oh, sorry, there's accent Z here. Okay, it gone. So again, this is cross-section view. Cross-section view. Section view. All right. Cross-section view. So now we are going to determine the total moment in this area. We know the total moment here is M, right? But the M also will equal to the dA, small dA, with the force acting on the small dA times its force arm, right? So you can see sigma x and times dA, they are force, right? And why is that? Why is arm? So you can imagine that there's a force. Can you see that? Sorry, I will make it. Can you see that? No? Okay, I will enlarge that for you. Can you see that? Okay. Okay, so this is the force. The force is sigma times dA pressing into the monitor. Okay, and the monitor, the force acting on that dA has the force arm y. So y times force will be moment. So this moment acting on this small area here is dm. small m, right? This is a small m. And then you need to integrate all the small dA in this cross section. And then totally it will equal to the m you applied on that subjective, on that cross section. Okay? So small bending moment on the small area is minus sigma xy times dA. And you do integration for that. And then you found that, so what is sigma x? Sigma x is kappa E y. So your y become squared. Okay? So again, kappa and E can go out to the integration sign. So here you can see another definition. Moment. Hey. Moment of inertia. Right? So your m equal to kappa EI. Okay? And your kappa equal to 1 over rho. So kappa equal to n over EI. And if you subject it to this, to the kappa, sigma equal to minus E kappa y, you will ends up minus my divided by I. So this is a really, really important formula. Sigma equal to minus my divided by I. Okay? Okay. Very important. 好，这边我觉得蛮重要，所以我用中文讲一次啊。就是我们刚刚不是把中性轴找到了吗？那我们知道然后我们知道sigma x 会是会是 kappa EY 嘛，对不对？好 ，kappa EY。那这时候 kappa 要怎么样跟 m 来扯上关系呢？因为 kappa 我们觉得很讨厌啊，它是曲率，很难算。那如果我们知道当那个材料的弯矩的话，那我们就可以取代 kappa， 就非常好。所以我们要做一件事情，就是说我们要去取代 kappa。那这时候我们就要去看看 m 是长什么样子。m 呢，其实这边就是每一个小底 a， 它自己有一个力嘛，去推它。那个推它会沿着一个轴去推它，它就会有力背，对不对？那这边就可以想象，就是如果今天有一个弯矩是从下面这样往上推 ，bending 它弯它的话，那这边就可以想象一下，这边是一个压进去的力量，压进荧幕的力量。压进荧幕的 stress 乘上底 A 就是它的力量嘛，这个力量往内往荧幕去戳它，然后它有一个力背，等于是说这一个小底 A 会想要去绕着这个中性轴去往荧幕里面去转，那这时候你就会去积分它上面所有的面积，那下面也是积分起来，因为反正这个东西没有 y 正 y 或负 y 的，因为它 y 这边就可以处理掉这个东西了，处理掉正负号方向的问题。所以总之呢，你每一个小面积，在这个截面积上的小面积的小弯矩，就会是这样子写。那把小弯矩全部积分起来，就会变成大弯矩。也就是说，这整个截面所接受到的弯矩 m。好了，那是 m 呢，就把这个式子带进去以后，然后把 kappa 1拿出去外面，积分符号的外面，我们就发现 留下来的积分符号基本上就是 moment of inertia 的定义，所以其实就是 kappa EI 啦。所以我们的 m 就等于 kappa EI 哦。那我们终于可以把刚刚很讨厌的 kappa 替代掉了，因为 kappa 就会等于 m 除以 EI。把我们的 m 除以 EI 带进去公式以后，发现我们的应力截面上的应力 ，OK， 截面上的应力会跟那个截面上所受到的 m 有关，也会跟这个应力在中性轴的高度的位置有关 y， 还有这个截面积的 moment of inertia I 有关，就这样 ，OK， 所以你就可以知道为什么第4章很重要了。第4章就是要告诉你怎么去算每一个材料的每一个位置的弯曲，因为你画了弯曲图，就可以算出每一个位置的弯曲，每一个截面的弯曲就是这个值啦。所以你画出 Chapter 4里面的那条线啊，你要看哪一个截面，你就去抓那个截面的图的值 m， 就可以带入这个值。然后你又可以去算你这一个截面上任意高度的每一个点的应力值，也就是说，这个材料的每个位置的点的应力值你都会算的。大概是这样子。这就是第5章难的地方，但是我也觉得是很厉害的地方。Okay, so that's the reason why we say chapter 4 is so important, because you see the stress, normal stress on a cross section is related to the value of the moment at that cross section. Actually, this value is actually from chapter 4, because you can draw the moment diagram, right? Moment diagram, and then you can see each cross section has different moment value. So that's where it comes from. Okay, and also the y here is that all the points at a different level of the height of the cross section, you can determine the corresponding stress. Okay, and also sigma will relate it to the moment of inertia of that cross section. That's it. So yeah, you can know the value of the sigma. Okay, so if you can understand this, you can determine the maxima stresses at a cross section. You can see that y can change, right? Y in this cross section, y can change. Of course. So now let's take a look. Anyone wants the bonus? Very easy this time. What is this? This is cross-section view or side view. So easy. Anyone, please? Cross-section view, exactly. What? Right. Can you tell me the feature you see that? How to determine this is the cross-section view? Y and Z axis, right? Good, very nice. When you see the Z axis, you definitely see the cross-section view. Okay, please tell me your number. 6. Sorry, can you louder? My ear is really bad. Oh, yes. 1308. 008. Yes? Okay, good. Well, it's very difficult because you also cover your mouth. So I cannot see your yeah. Sorry, I destroyed my ear when I was young. Okay. I joined well, I was in how to say that in English? Club, the club for rock and roll music band. Okay, so I destroyed my ear a long time ago. My friends at that period of time, the first words we say is 啊 ，yes， 听得懂吗？就是我在大学、高中的时候加入的就是热音社，然后所以就破坏了我的耳朵这样。 然后我们的那时候同才啊，就我们那时候朋友，我们每一次讲话一定都会讲啊，因为听不太懂，听不太到这样。那所以我们就只好就是需要用嘴巴的形状来去猜那个人的讲话，但你又把嘴巴盖起来，我猜不出来你在讲什么。然后这边又有这个啊，所以我听不太到，对不起，对不起。呀，对，还有时候就会吵架，就是他讲话听不到，就是他听不到，他以为我不理他这样。哎，总之就是大家好好保护自己的耳朵。我去健康检查，他就说我的耳朵好像是老人的耳朵吧，就是某个频率以上就是完全听不到，而且是那种断崖式下降，就是啊都听不到了这样，哎，都是真的。哎，所以那时候就是戴耳机啊，然后听音乐听很大声啊，然后或是去关在房间里面啊，鼓啊、吉他啊，哦，吵死了。但那时候觉得很爽啊，很好听这样。对啊，很开心就是。Okay, anyway, protect your ears. Otherwise, you uh, you cannot hear a lot of voice and sounds. All right. So this is cross section view. Cross section. Okay, so I don't need to write it down. Cross section view. Section. Okay. The maximal tensile and compressive stress occur further from the neutral axis. So you can see that sigma determined by M, Y, I. In the cross section, you see the I is fixed, right? The M is fixed because you has locate the cross section you focus, right? So the only thing you can change is Y. So how can you make the sigma maxima? Of course, Y maxima, right? So sigma 1 and sigma 2 means the maxima tensile, maxima compressive. C1 and C2, the furthest positive, furthest negative, basically this and that, all right? This and that. So for a rectangle, it is half edge, half edge, half minus edge. That's it, okay? So it's really simple. So the C1 means the top Y. The C2 means the bottom Y. Okay? C1 就是正的最大值 ，C2 就是负的最大值，就对了啊，简单。Okay? So your sigma 1 equal to minus MC1 divided by I. Your sigma 2 equal to MC2 divided by I. And you notice that C2 is minus, right? So minus and minus become positive. So this is the positive. All right? And you see that here, it gives us called section moduli. It called 剖面模数. I don't like this. Sorry, I don't like this definition. But well, this is a definition come from the textbook. I don't think this is it just gives you a one more parameters that you need to memorize. But I don't like this. Actually, S1 is actually I over C1. S2 is I over C2. Okay, I don't like this. 我很不喜欢这种特地给你一个新的符号，但实际上它就是 I 除以正的最大值 y 跟 I 除以负的最大值，就这样的。负的最大值 y 就这样的。Okay. And of course, you can see that the rectangular beam with height b and h, your s will be bh squared divided by 6. Your circular with the radius d will be pi d cube over 32. All right. So basically, the circular cross section, your C1 is here, the C2 is here. All right. Very well, easy. C1 equal to R. C1 equal to positive R. C2 equal to minus R. That's it. Okay. Next one will be a famous problem, and then I will draw that. I will continue that after 10 minutes. And if you have any question, just come here. Thank you. 然后我现在要去全家便利商店买饮料给我儿子喝，所以我希望我赶得回来，好不好？10分钟，加油！哎，有问题可以先来问，没有的话我就要去买饮料了。没有哈，好。 没办法，去买东西吗？啊，OK。喂，好，welcome back. So let's continue our lecture. Next one will be the examples, right? So you see that we need to find the figures, okay? And there's a what's that? Distributed load. Okay, this is distributed load, and this is A and B and C. Okay, and we need to determine what? Determine sigma T max, sigma C max. Okay, sigma T max, sigma C max means that the stress, the maximum stress for tensile and maximum compressive stress. Okay, so in this material, so we can mention that this material subjected to the distributed load Q equal to 3.2 Kn divided by M. And then we need to determine the maxima sigma T, maxima sigma C means that you need to see that if this material may break at certain point, okay, either tensile break or compression break. And you see, we need to draw the shear moment diagram. Okay, so I will skip this part because I have taught that, guide you to do that in chapter 4, right? So this is V, and this is M. Okay, so we need to know the sigma T max, sigma C max. Where will it be? Let's take a look. All right, so sigma T max, sigma C max, sigma equal to minus my divided by I, right? So in this position, I mean, in this cross section, it is rectangle. Sorry, did I say that? Did I say anything about the cross section? Oh, cross section is at the next page. Ta-da! The cross section looks like this. All right. So this is a very complicated cross section, but the cross section is prismatic. So this eye is fixed from the beginning to the end, from A point to B point. Okay, and we know that Y either C1 or C2, right? So if we want to find the maxima sigma, okay, we need to find the maxima M. The maxima M. Okay? So where is the maxima M? In this page, in this moment diagram. Where? Here, right? This is the maxima M. Maxima M. But I should say M positive. Okay? And because we also talk about compressive, right? So and tensile. So maybe you can see that moment positive M may resulting in tensile compression altogether, right? Also, negative will also give you positive sigma and negative sigma. So both of them are possibly to give you the sigma T max, sigma C max，这边有点重要哈，就是说，可能大家都觉得哦，我们要找一个最大的弯曲，哎，对对对，最大弯曲，那这时候看起来哦，m pos m 正的最大值 m 就好了，没有没有没有，你要注意哦，弯曲是 m 是正的，它会给你压应力，给你拉应力哦。那想 negative 也会啊，也会给你正大就是也会给你压应力跟拉应力，只是它反过来，也就是上面是压，上面是拉，下面是压嘛，对不对？negative 的，而且啊，我们的形状是长这样很奇怪，就是它的中性轴不一定是在最中间呐、哈，所以说你不确定哪一个才会给你最大值哦，哦这边要小心，我们等下就会看到。So which means that because either positive or negative m will give you tensile or compression, and also this shape is really difficult. It is complicated, so it doesn't it is not necessarily to have symmetry value of the y. Okay, so we need to be really careful. We need to discuss both of them. Otherwise, we cannot obtain a real sigma T max, sigma C max. Okay, now also based on the chapter 4, we know that m equal to 2.025 km dot m. Okay, and m negative equal to minus 30.6 km dot m. How can we know these two values? Because we learned the chapter 4, all right? So we need to get this by ourselves. Okay, now I'm going to draw a really big figures in this region, all right? We need to be careful because we know that our cross-section looks like this, all right? So I will give you a 3D, three-dimensional plotting, try to give you idea about this. X, Z, Z, and this is Y. All right, so I'm going to draw it. It's really difficult. Right. Okay. Okay. Oh, nice. Oh, very good. Okay. Oh, very difficult. Okay. Okay, so I hope you can understand what I'm drawing. Hey, yeah. 啊，不行。嘿，嘿，嘿，嘿。Okay, I hope you understand what I'm drawing. Uh, here is the hey, hey, hey. Okay. Yeah, more or less like this. So you can see this N pulse, and this is the N negative. And we are going to looking at the cross-section area. Okay, good. Can you understand what I'm drawing? I'm drawing a 3D, three-dimensional figures. You can see this, although it looks like a material with like a rectangle. No, actually, it's a kind of a how to say this? It's a cap. Okay, this is a 么字形要怎么讲? Okay, so this is shaped like this. All right, so you can see this, although it's not in scale. Okay, this surface is actually the side view of this. All right, and the cross section is in the next page. All right, and this is the distributed load, and this is the moment diagram corresponding to different position of that of this material. All right, and you can imagine that the two yellow cross section. The first yellow cross section is focused on impulse. So you can imagine that this cross section will has the impulse value moment, and this cross section has a negative and negative acting on that. And you can imagine that this impulse will compress the top and bending, tensile in the bottom, and vice versa. In contrast, by contrast, this negative section, this top will become tensile, and these two bottom will become compression. Okay, so we need to find these two shape has the which one has its own positive mix and compressive mix sigma. All right. 听得懂吗？就是我们现在已经找到有最大的正的弯曲跟最负的最大的负的弯曲。那这两个截面，这两个黄截面就正好对应到这两个点，它们的值的弯曲就会作用在这个截面上，一个是正的，一个是负的。那等一下下一页我们就是要去把这两个 截面分别去计算谁的正的应力跟负的应力谁大，就这样。好，谁正谁最正谁最负就对了。OK。So now we actually know how to determine the stress in a material, and we also know that which part will be the most dangerous part, weakness point in this material. So that's the why this course is important for the material. Otherwise, you don't know where is the weak point of your device. Okay. Now let's continue. Next page is really difficult. Okay, so let's focus on this more. It is a very classic example because you see chapter 4. So if I want to test you, I just give you a chapter 5 problem and then I can test you chapter 4 and chapter 5 all together. Okay. Next, two cross-section. Now, we are going to determine neutral axis. I will give you step-by-step way to determine neutral axis. Neutral axis. All right. Now, this axis actually they have some. It will give you some value from the problem. Okay, so the h equal to 80 millimeter, and and the b here b equal to 300 millimeter. Okay, and the t thickness is 12 millimeter. So this is the problem we gave you. The problem. The problem gives us the information. All right. Of course, this is also the thickness t equal to 12. Now, we need to determine the neutral axis of this cross-section area. It might be here or here or here. We don't know. Okay. So now, so actually we are going to determine the centroid of this material, centroid of this cross-section. Before we determine the centroid, we need to define a coordinate by ourselves. We can choose any coordinate by ourselves. We can choose here. We can choose here. We can choose here. We can choose here. All okay. But I will give you a smart choice. And maybe you will realize why later. Okay, I will choose this point, O plot. And you will know why I choose this. Okay, why I don't choose this? I want to choose it here. Why? You will know later. Okay, and of course, I will choose in the middle because this is symmetry, right? This is symmetry. So our y actually will be the middle. 因为这是左右对称的嘛，哈，所以我的这个 O plot 啊，哈，千万一定要弄在中间哈，不要弄在旁边一点点。中间为什么不用中间？因为它是一定要用中间，因为它是平，它是对称的，好，不要给自己找麻烦。Okay, so O plot we set there because it's symmetry, so don't make it biased to left or right. Don't do that. Okay, so yeah, make it simple. All right, now. But I am going to do it. I will define this whole plan and also why plot. Maybe you don't know why, but why plan? but it's okay. You will know that actually the plot axis, the starting coordinates can be set by yourself. You don't need to worry about this. Okay? So now we're going to find this complicated cross-section area centroid. All right. So there are three area: 1, 2, and 3. Okay. So the area one. Okay. So now we are going to take the area 1 centroid corresponding to O plane coordinates. All right. So here, y1. What is y1? T equals t divided by 2, which is 6 mm. Of course, right? You see, let me enlarge a bit here. Area 1 in this coordinates, okay, its centroid should be here, right? In the middle. So half 12 from O point. So it should be 6 millimeter. All right. So y1 equal to t over 2 equal to 6 millimeter. The area A1 equal to B minus 2t times t. It's easy, right? B 300 millimeter. B minus 2t, there are two thickness, and times the thickness itself. So you get 300 minus 2 times 12 times 12 equal to 3312 millimeter square. Okay, how about area 2? Area 2, y2 equal to where? y2 equal to y2, okay? Its centroid will add here is 80 divided by 2, 40, right? From the O plane. Okay? So h over 2 equal to 40 millimeter. How about A2? A2 is simple. HT equal to 80 times 12 equal to 960 millimeter square. And area 3 is similar to area 2. So we don't need to determine that yet. All right. Now, let's determine the neutral axis. Neutral axis here is centroid, right? So the centroid will be sigma yiai divided by sigma ai, right? So equal to 6 times 3312 plus 240 times 960. Okay, and yes. 3312 plus 2 times 960 equal to, let me using green 18.48 millimeter. Okay? So now 18.48 millimeter is the centroid coordinates corresponding to your O plot. Okay? So your real O here is here. It's called O, real O, real neutral axis, and it will distant by here is 18.48. 18.48. Okay? And so the distance between the O and your O plot is 18.48. Okay, so maybe you know why I set O plot at the top. Why? Because this is C1. Okay, C1. C1 equal to C1. The definition of a C1 is positive maxima. Why, right? How about C2? C2 equal to your H minus C1 equal to 80 minus 18.48 equal to 61.52 millimeter. So your C2 is C2 equal to 61.52. Okay, that's it. We successfully determine the neutral axis. Let me save some space. All right. Okay, C1, C2, done. So now we can totally forget the O plan, Z plan, Y plan. It doesn't matter, okay? So all we need to do is we need to know the distant difference between the real O and your O plan, okay? That's it. Now, very difficult, okay? Very difficult. Next one, you see that we know, I mean, okay, so we plot again. So here is your O, and here is your Y, and here is your Z. So now, after so much time here, we just start we just make sure one thing: the neutral axis here, and the distance here is 18.48.你看我们花那么多时间算那么多东西，我们只算出中性轴而已。然后那中性轴是在距离顶部18.48公里的地方，就这样而已。我们算那么久，就只能这样。所以你可以知道 Chapter 5超难，哦，超繁琐的哦。Okay, so you can see that how difficult, how complicated in Chapter 5. Very difficult. And I want to say that maybe someone will say, why we learn this so difficult things? And maybe it may not be useful in the future, right? Maybe you don't need to see that anymore after you graduate or after even pass this course. Why we need to do this? Why we need to learn all these complicated things? And it looks only important at this moment. maybe not important later. But I would like to say that all these difficult tasks you faced during the course, during your bachelor degree or master degree, is actually just like you training your body, training your muscle. You lift really heavy stuff and train your muscle. So then you will have the strong body and to face the more difficulty after you graduate. Okay, so I believe although this looks really difficult and it seems like only important here at this moment, but it kind of training your brain just like training your muscle by that weight. OK， 听得懂吗？就是练这个东西，我常常都会听学生讲说啊，这干嘛这么复杂，以后可能不会用到啊或什么的。那对啦，有可能，但是这个东西等于是帮助各位训练自己的脑力，去做一些很难的、很复杂的思考，就好像是你要去健身房去拿一个很重的东西去训练你的肌肉是一样的道理，让你会有很健康的身体。这样，那以后你去面对未来的困难，你就更多的基础去面对它。这样，那对啊，你看没事去举个30公斤的东西干嘛？那就是要让你自己身体变好嘛，对不对哈？举一个跟自己身体一样重的东西干嘛？平常不会去举这种东西啊，对不对哈？但是一旦你的身体习惯这件事情，那你平常遇到一些重量啊、困难啊，你都会比较好解决。好，这大概就是做这件事情的意义吧。OK，next. So now here is our sorry. This is our centroid, right? So this is our pink axis. This axis is our bending. This is our bending axis. All right. So we need to determine moment of inertia of this section. Don't forget this. Moment of inertia. Okay. Our moment of inertia is actually 3 IZ1, IZ2, IZ3, summed out together is a total I of this cross section. But the bad thing is that the first area has its own sorry, I shouldn't use pink. I should use green, right? I mean, yeah. And oh no, should be green. Yeah. Sorry. Should be pink. Should be pink. Yeah, because this is our target. This is our target. Remember that. Sorry. This is our target, right? We need to move from the centroid to the target axis that we actually bending about that axis. OK， 我们要去移动到我们真的要弯的那个轴。粉红色就是我们真的要弯这个轴，因为它就是这个截面的中性轴嘛，我们就是要对着它弯嘛，对不对哈 ？But we are going to rotate about this bending, rotate about this pink axis because this is neutral axis. However, all these small area, their centroid I is not here. For example, area 1 has its own axis here, right? So if you cannot see that, here. And area 2 and 3 actually, well, sorry, not really good. Higher a little bit. Okay, and the area 2 and 3 is actually here, right? You see, half of it. Okay, so we need to move parallel theory,平行轴定理 parallel axial theory. We need to move from this this I to the pink value, pink axis, and we need to move the purple axis to the pink axis. OK， 听得懂吗？就是粉红色是我们要真正转的轴，可是上面这个 area one 面积一，它的行星的轴，通过行星的转轴是在这里。那面积2跟3的通过行星转在这里，所以我们必须要移动它到粉红色的，移动它到粉红色，然后移动完以后得到值以后再全部加起来，就是这个解面积的轴 moment of inertia。OK， very very complicated, right? So IZ1 equal to IC1 plus A1 D1 squared. Did you see that the D1 is green, which means that 18.48. Well, sorry, I shouldn't. So sorry, -6. I shouldn't do that. I shouldn't use green, right? I should use yellow, maybe. Okay? Well, orange. D1 square. Okay? So it equal to half 1/12. 300 minus 2 times 12 times 12, 3. BH3 divided by 12 plus 3312 area, right? Area 1 times 18.48 minus 6 squared equal to 555,600. Okay, so this is area 1. Rotate about the pink axis. Its corresponding moment of inertia, IZ1. How about IZ2? IZ2, or you can say IZ3. IZ2 are the same. So it's IC2 and well, should I say C1 or C2? Maybe A1 or A2 is better, right? Yeah, I should make it A2. Otherwise, you will confused by the C1 and C2, right? A2. Sorry. A1. Area 1, area 2, all right? And this is the centroid of area 1 and area 2. Plus A2. Change another color again. A light green. Did you see that? Here. Okay, very small distance, light green. A2, D2, 2 equal to 1/12, 12, 83 plus 960 times 40 minus 18.48. 2. equal to 956,600 mm4. And of course, it is equal to IZ3 again. So the total IZ for the pink axis equal to IZ1 plus IZ2 plus IZ3 and equal to 2.469 times 10 to 6 millimeter 4. Okay. Again, we spend so much time and then we obtain IZ. We don't even try to determine the stress. So we spend so much time, and then we only gone to the second steps. Neutral axis, first step. Moment of inertia, second step. 有没有很累？就是我们做那么久，连应力都还没有算呢，我们只算了它的截面积的 property， 截面积的参数呢。哦，真心。真的太累了 ，very difficult。嗯，但我跟你讲过，如果我用直接在上面放大，然后写，跟我用，你看哦，我如果直接这样放大来写，跟我用这种 zoom in 的来写，zoom in 的写会比较好看，你知道吗？它这个可能解析度会有问题，就是你如果用下面那种加大的来写的话，它就会有这种，抑扬顿挫。但如果你今天直接写的话，你就会写的很丑。像你会发现，诶，像，嗯，这个箭头就是用放大的来写，但这个箭头就是用直接写，你就会发现它的那个笔触就不会有这种那种渐渐的变尖的感觉。哦，所以我觉得哇，这个一定要写字一定要放大的来写才会好看。像刚刚，例如说大家讲那个加分的那种班号的时候，我基本上都是直接写，所以我加分的班号都会写比较丑。但如果今天是用写式子的话，我就是用放大的来写，那就会比较好看。这样，我这个人比较龟毛一点。实际上啊，哈，我觉得以前的，就是 Apple Pencil 的这种按压的好看程度，并没有比以前的还要好。以前的我用不就是怎么样那种非主动式的触控笔写的字，我觉得会更好看。我也不知道为什么，比这个还要好看。那但是没办法，因为这手可以放在上面，太香了，所以我还是用这个。不然的话，以前我用那种外面卖的，不是 Apple Pencil 的触控笔，然后我就必须要选完写，然后哇就会写得更好看，但是就好累啊。OK, I just saying that the Apple Pencil is quite nice. Right. Next, final stage. Final stage. Now, after we determine the I and C1 and C2, we need to determine uh, see, this is not enlarged. But if I enlarged, see, very different. Okay, and Z Z toward you, okay? Toward you. I'm going to draw this, and I will give you a chance to have a bonus. Okay? What view I'm drawing now? What view I'm drawing now? Anyone? 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 What view? Side view or cross-section view? Side view, exactly. Why? Because y-axis on the plan, right? Z toward you. Very nice. This is side view. Side view. Please tell me your number. Okay, thank you very much. Okay, we are going to examine part M positive or M negative. Okay, so you can imagine that this is side view, right? So it will make it smiling curve for the positive and prime curve for negative. And of course, here will be compression, right? And here will be tensile. And of course, here is tensile. And here will be compression. All right. And again, dot, 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 dot. This is the neutral axis. So it will be the same before and after bending. So this is C1, C2, C1, C2. Okay. So now we are going to determine sigma T and equal to minus M positive times C2 divided by IZ. And we also want to determine sigma C minus M pos C1 divided by IZ. Yeah? And next, we are going to determine sigma T equal to negative M negative C1 IZ. Sigma C negative M negative C2 IZ. Yes. I guess I don't have time to finish all the value, but I will tell you the result. This is 50.5, and this is minus 15.2, and this is equal to 26.9, and this is minus 89.8. Okay, so you see that maxima T here, maxima C here. Okay, well, I will finish that tomorrow. All right, I will see you tomorrow. Thank you. If you have any questions, just come here. Okay. Yeah, very difficult. I know that.
问，请问
那前面的问题，前面的 PPT 好，我看大家都应该好，请说。
是那个你说那个第一两个新的传输那容，
新的那个 S1这个请说。
那个为什么跟这边的不，就是跟我们之前的教授有关？
一个是 R 吗？等一下，
说什么一个就是
这是极惯序，所以是极坐标，是圆坐标。它是对于 O 这个轴在转。那如果你今天是对于 Z 轴转的话，是
它的算法，
也就是说，一个是这样转，一个是这样转。所以现在看的东西是这样转，是沿着这个轴转。那之前你说的极坐标是这样转，对，是这样转，圆心转，所以是不一样的。谢谢，好问题。好，我通常都是第5章教完就会小考，然后期末考就是第7章教完，所以期末考应该就是期末考周。谢谢。